conjecture, and I will spend some time explaining it and trying to make some propaganda for this conjecture. Yeah, so the conjecture is that if I take a generic curve together with a half period in genus 2i plus 6, general. Yeah, so this is an irreducible space, so it has a meaning to say that it's general. Then the prime canonical bundle k plus eta satisfies property Ni. And of course, I can state this also in terms of Kosul cohomology groups. So this is completely equivalent. I can say that ki2 of k plus eta is 0, where this is the Kosul cohomology group. Yeah, so which is obtained from a complex, I mean, just the sake of completeness here, so y wedge I A0 L, well, L is k plus eta. Tensor A0 L squared goes into wedge I minus 1 A0 L tensor A0 L cubed. And here is the wedge I minus wedge I plus 1. Yeah, so L is k plus eta. And this is so kij, so this is di2, and this is di plus 1, 1. So the Kosul cohomology group, ki2, by definition, is the kernel of di2 by the image of di plus 1, 1. But of course, this algebraic machinery only hides the fact, I mean, the geometric meaning of is that the syzygies of the prime canonical, generic prime canonical curve are as simple as they can be for I steps. The conjecture is absolutely sharp in the sense that I made a conjecture. This is the conjecture. If
I'm sorry, I is the same.
Yes. So the conjecture is sharp in the sense that the failure locus is a divisor. It could be the whole variety, and then the conjecture is false, right? So this is, of course, inspired by the Green conjecture, by the classical Green conjecture.
I'm sorry, to ask you a kind of general question.
Yes.
Does this depend, I mean, if you make exactly the same question for any divisor of degree 2g minus 2?
Very good, very good. Right, that's very good.
Or are you going to use the fact that eta is?
Very good. But let me finish this sentence. So the Green conjecture, right, is that if you take G equals at least the generic form, right, is 2i plus 3, then Kc, so C now is generic of genus 2i plus 3, then Kc satisfies Ni. Or in other words, Ki2 of CKC is 0. So this is, of course, more is now, we know the failure locus. The failure locus is this divisor, is the Hurwitz divisor of curves with a pencil of degree I plus 2. So this is exactly what was improved. Yes? Her proof of the generic Green conjecture, and this is also sharp in the sense that you cannot improve it. You cannot hope that you can replace here by I plus 1. You also know that the conjecture fails in moduli as much as it could fail in the sense that the degeneracy locus is, that the failure locus is a divisor, right? And in fact, you can use Green's conjecture. I mean, so as I said, I have a paper on arXiv last year where this can be, I mean, this approach using Green's conjecture is carried out to give a very short proof of the Harris-Mumford theorem on the general tightness of Mg. It's really all this stuff about admissible covers and intersection theory on the stack is this kind of 60, 70 pages of calculation. It's completely reduced to 5 pages, but of course, the difficulty goes into Voisin's paper. If you assume this paper, then the proof of Harris-Mumford becomes very easy. But this is not easy. I'm not saying that. So, okay, so the conjecture is a general analog of that, and Meyer's question is indeed very good because there is an easier version of the conjecture. I make this conjecture as well, so easier than Prim Green. And now I make it like this. If I take C and, well, I'm going to write it K plus a bundle of degree 0 because I prefer. But so this is a generic in the universal Picard variety of degree 2G minus 2, right? So this is universal Picard. This is irreducible variety. Then I conjecture that K plus eta satisfies an I. This is also open. So honestly, the Prim-Green conjecture looks extremely difficult at the moment. It looks much more difficult than the original Green conjecture because you have all the problems from the original Green conjecture, plus you have this very non-geometric condition of the point of order 2. So the Prim-Green conjecture is a refinement of this in the sense that I say that the failure locus in the universal Picard variety does not contain the order 2 locus. And I can make the same conjecture for any level, in fact. So in any case, to prove, so this is the, yeah, maybe I should say what the conjecture is.
So
what?
this easier version would not follow somehow?
No.
Easily from the Green's conjecture?
Absolutely not. It is, no. It is a that's what I meant when I said it's a sharp version. You can prove weaker versions. I can imagine to prove a weaker version of.
If something is true for K,
No, because.
No, these paracanonical guys are smaller than K.
Yes, exactly. The generic, you should not take here 0. Then if you take 0, then you are not even in the right projective space. You are in PG minus 1 as opposed to PG minus 2. Right? So that's, yeah, that's, it's not, and it's also, it doesn't follow by a degeneration argument. So we know now that Voisin's theorem is true in a degenerate form, for instance, for curves like this. And you say, okay, maybe I do the normalization of such a curve, and then I pull a canonical bundle from here, but it doesn't work. It's really a sharp statement in the sense that you really, it looks as difficult as Green's conjecture, and in fact, this looks much more difficult than to capture this level 2 thing. But let me just explain the conjecture. So I find it's kind of an interesting statement, and to motivate us, so I should look at I equals 0. So you know that the classical Green conjecture, this was a generalization due to Green of classical statements of Max Noether and Enriquez, Petri. Yeah, classical theorems. So what is the Prim-Green conjecture in small genus? So this was for genus 3 and genus 5. For I equals 0, genus 6. So I look at the Prim canonical curve so this is K plus eta. This takes me to P4, and this is given by a G4 10. And the conjecture is that this satisfies N0, which is projective normality. And so I look at the map from Sim2 of H0 K plus eta into H0 of 2K. Yeah, remember that eta square is trivial. And the dimensions of these are both 15. And the conjecture is that, the Prim-Green conjecture is that for C eta generic, C sits on no quadrics. So C sits what? Sits on no quadrics. So it's a sharp statement, right? Is that this map is an isomorphism. That's what I'm conjecturing. And this conjecture is equivalent to infinitesimal Prim Torelli. So because so that is equivalent to saying that the differential of the Prim map from R6 to A5 is generically 1-to-1. Because the differential, this is exactly the co-differential of the Prim map. That is due to I suppose to Beauville, if not before. This is the co-differential of Prim. Right? I mean, I hope you recognize, so this is certainly the tangent space to the cotangent space to the moduli space of curves, and this is the cotangent space to the moduli space of abelian varieties, right? And then I'm saying that this map is injective. It's isomorphism. And so this Priem conjecture in genus 6 is known. And it appears in Beauville's paper on the Schottky problem. For I equals 1, genus is 8. Then I have now my curve in P6. So this is a G6 14. And now I'm saying it satisfies N1. So now I look at at the generation by quadrics, and then I have this is the space of quadrics containing. I already know that C is projectively normal, so I know how many quadrics and cubics are there. And I look at the map. So these are the cubics containing the canonical curve. And again, now you compute by Riemann Roch. I haven't done this, and they have the same dimension, hopefully. So the same dimension, and the conjecture is that this is an isomorphism for C eta generic. And this is equivalent to, so the first one was the infinitesimal Priem Torelli. So this was infinitesimal, I don't think I wrote it down. So this was infinitesimal Priem Torelli. And in fact, this is due to, this is the Priem Torelli theorem itself in genus 8. This is, it's not entirely obvious how this is, that this is equivalent to Priem Torelli, but this follows from work of Debar. And in fact, Debar proved this theorem in genus 8.
Generic.
Yes. Oh, the conjecture is also for a generic pair, right? So it is there are two very interesting statements, right? This is an infinitesimal Priem Torelli, and this is the Priem Torelli itself in small genus. So I kind of see the analog. Well, so okay, so these gentlemen are not as old as Max Noether and Enriquez, but it is an interesting statement, and in some sense mirrors the situation for what happens for the canonical curve. So also for the purpose of the theorem, we only have to prove this Priem-Green conjecture I mean, the statement is as it is. I don't have really a good plan of how to prove it in general, but this is a theorem. So, and this is due to with Schreier, with Frank Schreier, that the conjecture is true for genus up to 18. So Priem-Green conjecture is true for genus up to 18. So to my mind, this is rather compelling evidence. And in particular, it proves that, the Priem-Green conjecture in bounded genus has implication on the birational type of RG. And it proves that RG, I mean, put together with the other theorem about the class, that RG is of general type for G greater than 14. And it has positive Kodaira dimension for genus greater than 0. So, I mean, let me just discuss. Yeah.
Your method would be different for genus greater than 20?
Well, so I will just show how this is done for genus 12, and then you will this will answer your question. I mean, this is, of course, the calculation itself. This uses computers. This uses computers very heavily. And you cannot really prove for arbitrary genus like this. Also because you cannot write down the curve of genus G for arbitrary G. So all these conjectures are true. I mean, it's enough to produce a single curve which satisfies the conjecture, right? So it's enough to produce, so to exhibit a C and eta such that if I now put my curve, I will do genus 12, but the other case is a sort of a similar, except worse. It's in P10, and this is now a G10, 20, 22, which satisfies N3. So the problem, of course, is there are lots of ways of producing this curve of genus 12 in P10, but this condition of the point of order 2, this is very hard to realize geometrically. And there are various possibilities, but what we did in this case was to go for a plane model. So the numerology is not so important, but just maybe I will explain in principle how you can check such a conjecture. So the idea is to look at a plane model of a curve of genus 12 with triple points. So this we did after many tries and failures. So I look at a curve. So I look at a curve of genus 10, which has a plane model of degree 10 with, and now you count with 8 triple points. So these are the triple points, pi. And now I have to create, you can calculate the genus of this guy, is 36 minus 24, 12. And now you have to create somehow the points of order 2. And the points of order 2 will be, the point of order 2 will be created by another curve, another plane curve, which will happen to have degree 6. So this will be another curve, two curves, Z6. These will be curves of degree 6, which have nodes at, so 8 nodal curves of degree 6 with nodes exactly at the points pi. So now I will just put here with another color. So this is Z, and this is gamma. Yeah, and then I want the point of order 2 to be obtained as by some common tangencies. So now I'm going to write here plus minus. I will write here 2 times the sum of Li. But by this I mean for 1 to 6. By this I mean common tangencies. These are no nodes. That's why I wrote them in blue. I don't know how to write this. So this is common tangencies with gamma. And so gamma itself also will have this tangency at this point, right? And then I want another curve with the same properties. So I have a curve Z6 prime, which have the same properties, nodes at the same point, and tangency at some other points. So these points are Li prime. Now I hope you see that there's no hope of doing this for arbitrary genus. The point of order 2 will be now the sum. So of course now these curves will sort of, you can see what's going on. So later on these curves will have a common tangency at some of these points, right? And this will be one of these points Li 6 times. And then you do this, you see the intersection numbers. I mean, so this is 60 by Bezout. 60 is 8 times 6 plus 12, so it matches. The point of order 2 on gamma will be, eta will be the sum of the Li's minus the sum of the Li prime. And then, so this is a point of order 2. So this is in peak 0 C of order 2 on the normalization. And now everything is very explicit. The curve C is a plane curve, so the canonical linear system you can understand. The point of order 2 is explicit. And now with Macaulay, you use Macaulay in an absolutely fundamental way to check the syzygies of this curve. And the way you do it, I'm sorry, I'm sort of maybe going too much over this calculation, but so kind of maybe I just have not enough experience with such things that I'm so easily impressed by a Macaulay calculation. But you first construct Z and Z prime as 8 nodal curves with random points, and you take random tangent lines, and then you construct at the end your gamma as an 8 nodal curve with 8 triple points and 12 fixed tangencies. And this is hard. I mean that you have to do over finite characteristic, and because these are too many conditions here. You have 8 points, 8 triple points, and 12 tangencies. It is a codimension 7 condition on the space of all plane curves, and finding one example takes about 18 hours, and then you in the end you find one which has the right syzygies. So this proves the conjecture. So that is, yeah, this is, as I said, this is something that you can do in bounded genus, not in arbitrary genus, but it proves a conjecture for genus up to 18, and this is all I needed for this general type result. Yeah. Okay. And so then there is a little lifting argument from characteristic P, characteristic 5 in this case, to characteristic 0, which I will not mention now. Yes, right. Yeah, so it's a transversality thing. I mean, this is, yeah. So it's kind of difficult to find also this, somehow these curves have too few points. If you increase the characteristic, then the calculation becomes too long. I mean, then actually it just crashes.
If you do computer algebra, you take finite field, order about 1,000. You take random elements, and then you delete the
Well, I would have certainly not have done this in bounded time myself. So that's there is no doubt about that. Okay, so that's about it about this general typeness. And so now, since I'm still with RG, I would so remember that I go from the other genus. From the other end of the spectrum, from small genus towards high genus. So we know that RG is uniruled, or actually unirational, for genus less than or equal to 7. And general type for genus, let's say 12 or 13, right? And codaya dimension at least 0 for genus 12. But this is a considerable gap in between. And so I tried to look at the situation, and basically what I could prove together with Alessandro Vera is the following theorem. So joint with Vera that in the next case R8 is uniruled. And it's also a kind of a pleasant, it's a modular parametrization, if you wish, of this space, so I wish to talk about this. Yeah. Except that. So the construction, we don't really prove that R8 is uniruled. We prove that a certain auxiliary moduli space, which maps dominantly over R8, is uniruled. And this space uses a little bit of the theory of the singularities of prime theta divisors. So remember, let's say if I take a point C8 as this is, I will do it in general, and I will specialize to genus 8 only at the very end. Then this corresponds to a double cover, an étal double cover. So this is étal 2 to 1. And then I had these norm maps, right? Which were important in the singularity theory of the theta divisor. And I considered already essentially now I can consider this loci VR of C8, if you wish. So these are the loci L in the inverse image of the canonical bundle with the property that H0 of L has at least R+1 sections and the parity is constant. So going back to Mumford, I suppose, or Mumford-Welters, these are skew-symmetric degeneracy loci. And of course, you can, just like by analogy with classical Brie-Noether theory, you can develop a deformation theory for these spaces. And you know that the tangent space, the cotangent space rather, to VR is, yeah, so I should say something else. So to such an object, you can also associate the Petri map. So to such an L, you can look at the multiplication map. So this is the Petri map. So this is a map which comes from A0L tensor A0 KC tilde minus L into A0 KC tilde. This is the map which governs the deformation theory of sections of line bound laws. Now the point is that I have this condition that the norm is canonical. So I know that this condition is equivalent to saying that K minus L is just I pullback of L, where I is the involution. So I is the involution. And then I have that, so the norm is canonical. This is, of course, equivalent to saying that L is I pullback of L is Kc minus L. So I have, you see now that basically this is A0L tensor A0L, and there is a Z2 action on the prim map. And again, it has two eigenspaces. And the prim map factors into a plus map and a minus map. So I have here a plus map, which is the map given from essentially from scene 2 of A0L. And here I have also plus minus action, right? So I look at the plus 1 space of A0 of K tilde, and this is A0 of KC. These are the differential coming from the base. And there is also a minus map. And this maps wedge 2 of A0L into A0 into the minus part of this space, and this is A0 of K plus eta. So these are the prim Petri maps, if you wish. They are completely, I hope it's clear how they are defined, right? So then I just symmetrize sections and then kind of anti-symmetrize them. Okay, so what is known is that the cotangent space to this locus VR is the cocanal of the minus Petri map, prim Petri map. Yeah, this is really a basic theory. What is not so basic is the theorem of Welter's, that generically, I mean, for a generic pair, this map is always injected. Yeah, so Welter's proved that for C eta in RG generic, mu 0 minus of L is always injected for any L. So in particular, it follows then that the dimension of this locus VR is smooth, and the dimension of VR is G minus 1, right, minus R plus 1 choose 2. And this, you see this Q-symmetric degeneracy locus structure on this locus, on this subvariety of the Jacobian. Okay, so now the idea, so right, I already explained that if you want to look at the V, essentially the prim variety itself is V minus 1 for R equals minus 1. And for R equals 1, you look at a single locus of the theta. And most people study this loci for odd even, for odd R, right? Then you really get you are on the positive part of the prim variety, of the kernel of this map. But so our idea is here to study instead the even part, and to look at V2, and to look at this auxiliary moduli space RG2. So this is the moduli space parameterizing pair triples C eta L, where C eta is in RG, and L is in V2 of C eta. And of course, this maps onto RG with fibers of dimension G minus 4. Right? G minus 1 minus 3. G minus 4 dimensional fibers. So this is some auxiliary moduli space which will allow you to give some projective geometry, to construct some, to have some projective geometry that you can associate to this prime curve. Okay.
Sorry, are we talking about the singular locus of the theta?
No, we are not, because that would be for V1. I'm looking on the even on the odd part of the prime variety, right, where I have always this doesn't have a nice interpretation of the in terms of singular locus of theta divisor. That's why it was not so studied before.
It's a locus inside.
This is a locus inside, so V2 of course is inside V0. But since I'm shifted by 1, this is the odd part of the.
We're in pick 0.
We are in pick 0, but with one section. We are in pick 2G minus 2 with one section. Yeah. So what I said at the beginning was that V minus 1, this is the prim, and V1 was the singular locus of the theta. But this was for R congruent to 1 modulo 2. But now I go on the other side. I look on the other copy, which does not have this nice interpretation of the theta divisor and of singular locus. Right? So this part was not so studied for this reason, right? So the question is, do you work with the odd or with the even prime Petri map? Okay, so out of this picture, I'm going to present a general construction which goes back in some sense to Catanese, which will basically a general construction for a generic point of RG2. And I'll see how far does this take us. So I will fix now, so let me fix now such a triple C, eta, L in RG2. So I have a prime curve and a line bundle which is almost invariant and which has 3 sections. So to this I can embed this curve now into a product of P2 with itself by looking at this, by using the sections of L and I pull back of L. Yeah, so I'm in P2 cross P2, and so I take the sections, and of course this embeds via the Segre map to P8. So this is P of this is P of A0L tensor a product P of A0 I pull back of L, right? And this is basically P of the tensor product. So I can project, so this is actually a map. I can project to the symmetric tensors. So here I end up in P5, and this P5,
L is on C or C2?
of course in CT dot, thank you. So this is P5, and this is P of sim2 of A0L. So this is exactly the guy that comes here in the plus part of the Petri map. Now the map here is of course 2 to 1, and it factors through C. So here is C, this is the covering, and here I have this map. It's given, it's a sub-linear series of the canonical system, and it is given exactly by the image of the symmetric prime Petri map. So I have this diagram here. So I have now this map here. Let's call this map S, and this map is 2 to 1. So this map appeared yesterday in Laza's talk. The image of this map is, of course, the symmetric, I will call it D, divisor, is the symmetric cubic hypersurface, determinantal cubic hypersurface, which is the secant variety. This is basic algebraic geometry, secant variety of the Veronese. And the singular locus is the Veronese itself. So the singular locus of D is codimension 2 is the Veronese surface. So the point here is that any element, what is the point, what is the role played by this line bundle L? Any element in RG2 can be, any curve in RG2 can be embedded in P5 so that it sits on this cubic hypersurface, on the singular cubic hypersurface. And of course, I can reconstruct via this covering, via this quasi-étale covering, this étale in codimension 2, I can reconstruct the not only C, but also the point of order 2. Okay, so that is something that essentially, I think, Catanese in his proof of the rationality of R4 sort of used this for the first time. But now come, so our idea to prove uniruledness here is to try to put this prim curve on a canonical surface in P5. Basically, if you put it on a canonical surface, you have to put it on a surface so that it moves in its linear system. And since it's a canonical curve, if you put it on a canonical surface, you will achieve this. So the strategy. So what canonical surface? We are going to take a very simple canonical surface, embed C. C is already in P5 via this map mu 0 plus into a 2 to 3 complete intersection. So let's call this S in P5. The point, of course, is that Ks is OS of 1. And then if I just write down the usual exact sequence, so I have something like OC of C. Now, by the adjunction formula, this becomes trivial, right? And this will move now. So you see that the dimension of the linear system is 1. Yes, by just taking cohomology. So essentially, you get a uniruled parametrization of RG2. Well, I mean, you don't have so much room, right? Because you are forced to be in P5 by this construction, and that is the most reasonable, the easiest, certainly, canonical surface that you can consider in P5 is this 2 to 3 complete intersection. So you already have this cubic, right? This is very good. You need 2 quadrics. So you have to count how many quadrics. When is this possible? So you have to count how many quadrics contain C in this embedding. Well, this is not a, let me call the image. Let me call, so W, let's call this space S2 of H0L. So this is a 6-dimensional space. So now I have to look at the multiplication map from sim2 of W into H0 of K squared. Right? So remember that this is a subspace of the canonical line bundle. Right? So that's why I put here H0 of K squared. And I count dimensions now. And of course, I get on both sides 21. So this is a 7 choose 2, which is 21. And this is 3G minus 3. OK, so now I'm going to use that G is equal to 8. Yeah, sorry about that. So G is equal to 8 now. G is equal to this is 21. So in general, there are no quadrics at all. But you see, for genus 8, I have a 4-dimensional fiber here. I have exactly 4 degrees of freedom for my construction. And now if I require to have 2 extra quadrics, when I look at this map between vector spaces of the same dimension 21, having, so let's call this map mu, the condition that the co-rank of mu is greater or equal to 2 is expected as a codimension 4 condition inside RG2, RA2, yeah? So you expect to find a codimension 4 variety here, which will map dominantly onto RG, and for each point in this variety, there will be a rational curve passing through a general point. And this will give a uniruled parametrization of R8. So let's try to write this down. right? So essentially, I can view this map as a map of vector bundles over RG2 of the same rank, and then I can define this locus Z. So this is the locus of triple C eta L in RG2 with the property that the co-rank of mu at this point is greater than 2. So this is a subvariety of RG2. Of codimension 4. And of course, RG2 maps onto RG with 4-dimensional fibers. And then the hope is that this will be dominant. Yeah? This will be dominant. So you know that the codimension of Z in RG2 is at most 4 because of it's a determinantal variety. But of course, things could still go wrong. Yes, you could still have positive dimensional fibers here, and then the map will not fill RG, but in fact a smaller subvariety. So what you have to prove here is, and that is, if you do this, then you are done by this argument, is that there exists an isolated fiber. So if I call this map phi an isolated fiber of phi restricted to Z. And if you are done, then if you do this, then you know that you have really parameterized the entire R8, and you basically the generic point of this Z will lie on such a canonical surface. It's not a smooth surface, of course. So then this Z for C eta L in Z. So C will lie on this intersection of two quadrics together with this cubic. This is in P5. And now this is a canonical surface. This is my S, and the singular locus of S consists of, so is the intersection of the Veronese with two quadrics. So this is, I suppose, 12 points. Yeah, so you prove that this is a kind of really, this has 12 nodes. But the hardest part, of course, is to prove this, right? To find, this is a kind of a similar statement to the one for the Prim-Green conjecture, to find one example where the fiber is zero-dimensional. At least it has an isolated point. So that is the story in genus 8, and it is also clear that this proof doesn't go any further, right? So you cannot.
It doesn't go that. Does it automatically prove R6?
Yes, right. Yes, absolutely. So actually, that's so. Vera's original of proof, still unpublished proof of unirationality of R7 is the same idea. But then you go a little further, he actually proves unirationality. So for R8, you don't have, I mean, he looks at linkage. I mean, he goes on and on, essentially. He takes this picture, I mean, they have different parameters, and then you look at essentially the linked curve, and then he shows that linked moduli space is unirational, and then it follows that R7 is unirational. But for R8, you no longer have room for this. You can only do uniruledness, because really, what you show is that you have a codimension 4 subvariety in this auxiliary space, which is uniruled. So for higher G, of course, you will have just subvarieties. Okay. So that is the situation regarding the moduli space of curves with the Prim structure. So I still have a little more than 15 minutes. So I wanted to talk about 1 hour about the pre-moduli space and 1 hour about the spin moduli space. And the discussion about the spin moduli space will be shorter now. Of course, there is an entirely parallel story about the moduli space SG, which is the spin moduli space, the moduli space of spin curves. So this is the pairs C, now let's call theta, where theta is a theta characteristic. And this splits into two connected components, SG plus and SG minus, corresponding to the parity of the theta characteristic. Yes, this is well known. And the degrees, of course, are also well known. The degrees of the number of theta, of even and odd theta characteristics. And Mumford proved that theta characteristics do not mix in parity. I mean, odd ones do not become even and vice versa. And you have this very interesting moduli space, the spin moduli space, which you can ask now. Large parts of the talk would have to be repeated, and of course I'm not going to do that. You have a nice compactification, is similar in style, very similar to the moduli space of prim curves. And you can ask yourself, what about this moduli space? So here for SG, the reasons for studying this are more modern in some sense. So you don't have this gorgeous picture related to the prim map and rationality questions. Instead, you have intersection theory. These spaces have very nice intersection theory. In some sense, at least as nice as MG itself. The higher level moduli spaces, they are subject to a very nice conjecture of Witten. And also, these are the spaces on which theta functions and global coordinates, it's a kind of a minimal compactification of MG on which certain modular forms make sense. For instance, if you follow the string theory part of archive, so these people who do kind of a heterotic string amplitudes, basically want to write down modular forms on the moduli space of curves, satisfying various astonishing factorization properties. All those problems are posed on SG. So the questions, of course, are the same questions. How about this moduli space? Can you sort of classify this? And so in this case, so I have looked first by myself and then in joint work with Vera at this situation, and rather surprisingly, here there are absolutely complete results. This is far from being the case for RG. So I will just mention these results. So first one, this is my theorem from last year, which is now actually in print, that the moduli space, the plus moduli space, the plus moduli space is a uni-ruled variety for genus less than 8, again 8, but strictly less than 8. But then comes something surprising. It's a variety of general type for G greater than 8. And then, so this is joint work with Alessandro Verra. So hopefully this will be on the archive before the German semester begins. SG minus is, so we know it's actually unirational for genus less than or equal to 9. It's uni-ruled for genus 10 and 11. And it is of general type for genus greater than 12. So this is complete. And the nature of the moduli space changes exactly at genus 12, if you wish. And then, of course, here there is a gap, right? There is a gap. So perhaps it's a little surprising that this general typeness is very different. And, well, you can also see that there are genera where one component of the spin moduli space is of general type, and the other one is unirational even. Yeah, this is kind of surprising. So the gap here is in genus 8. And then I would want to talk about this. So we managed to settle this one as well. And so we proved that the Kodaira dimension of S8 plus is 0. So S8 plus, in fact, S8 plus is a Calabi object. Yes? So,
Meaning that the canonical is trivial?
well, the canonical is not trivial, of course, but it has there is a unique form, there is a representative, and that doesn't move, and then the other vanishing conditions are satisfied. So, as far as I know, this is the first example of a natural moduli space which has intermediate type, which has intermediate Kodaira dimension. This is a kind of a very strange effect that this shift from rationality to general typeness is always very sudden, and it completely bypasses the intermediate cases, unless you look at some very artificial constructions when it's obvious that you are going to get something of Kodaira dimension 0, for instance, like elliptic curves, moduli space is M1n. But this is the first one where this is really something non-trivial goes on. And yeah, so I will briefly talk about this, the proof of this theorem. So since especially the other case for RG was also genus 8. So yeah, of course, I mean, a lot of the definition of the space and the definition of boundary divisors is somehow similar. And also the singularity study, this was carried out a couple of years ago by Katharina Ludwig. It was, in fact, she did the SG before RG. And what I should say is that we know, I mean, from my previous work, it was clear that the Kodaira dimension of S8 was at least 0. And the canonical bundle of S8, there was a kind of a distinguished representative of the canonical bundle. So on SG, there is a distinguished divisor on SG plus. And this is the theta null divisor. So this is the locus of those curves with an even theta characteristic, which have sections. And then they have two sections. Yeah? So this is a classical divisor. It was considered long before. Of course, this is equivalent to saying that if I look at the canonical embedding of the curve, the canonical embedding lies on the rank 3 quadric, right? So C theta is in theta null. If and only if there exists a rank 3 quadric in PG minus 1, which does not meet the singular locus of the curve does not meet the singular locus of the quadric. And then, of course, the ruling of this quadric, the only ruling of the quadric will be the vanishing theta null. So I have computed the class of the compactification of this divisor, and this is how this theorem is proved, in fact. So this is an incredibly effective divisor. And so that is one main character on the SG moduli space. And then there is another one. Namely a Brill-Noether divisor. Then there is also, actually on M8, there is a Brill-Noether divisor. And this is the locus which I call M8 to 7. So this is the locus of curves which have a G to 7. Septics. Septics with 7 nodes. So this is a divisor. That's clearly a divisor, irreducible divisor. And the class of this is known. And so what follows from essentially this earlier work on SG and on the class of theta null is that there are constants. There is a constant alpha such that the canonical bundle of S8 is 8 times. Well, this 8 plays really no role. I'm just going to write it here. The theta null divisor plus a certain constant, which is also explicitly known, of the pullback of this locus of septics. Right? So this guy, the locus of septics, the septic divisor lies on MG, so I pull it back to S8. And then plus some combination of boundary divisors. So here I should just write AI alpha I plus BI beta I, where AI, BI are positive numbers, rational numbers. And the alpha I, BI did not define them, but these are the pullbacks So here I have, inside MG, I have the locus of divisors of compact type, of type delta I, and then I have that the pullback of delta I splits in two components. And these are exactly the alpha I and the beta I. They will not play any role. This you can freely discard this. So now you have this canonical divisor, canonical representative of SG. And so this is, you found that the Kodaira dimension is at least 0, so alpha is positive. And the point is now that, first of all, you prove that none of these divisors will move. It's quite clear that these guys they have anti-Neff normal bundle, they will not move. It's also clear that this doesn't move, and then you can prove that this doesn't move. But of course, the sum could still move. So the crucial part, so what we want to show to prove this theorem is that essentially any multiple of this linear system is rigid. So there are a couple of ingredients, I mean 2 ingredients here. The first one is the most important. You basically show that through a general point, C theta, I suppose, in the theta null divisor, there is a rational curve R in S8 plus, which has the following number of remarkable properties. It intersects the theta null divisor negatively. And it completely avoids the other guys. It intersects 0, the locus of septics, and it is actually physically disjoint from these boundary divisors. So if you do this, then of course that means that you can simply, out of this linear system, you can take out the theta null completely. You can just remove this theta null, right? And because any multiple of the canonical bundle will contain the theta null divisor, exactly this many, will contain the theta null divisor plus something else. So that implies that n times the canonical class of SG is in fact equal to A times n theta null plus the linear system. Minus this thing. And now you are left with proving that this linear system has Kodaira dimension 0. And this is now sort of easier. So here now you prove that through a general point, I mean essentially through a general point of the septic locus, there is a curve. It's not a rational curve, but it's a curve, T now, such that T intersects this pullback negatively. And T intersects alpha I and beta I 0. So then you iterate, and you can also remove this one. And then you are left only with the boundary divisors, and those are kind of clear because the normal bundle has negativity properties that don't move at all.
Are there some natural birational maps that contract those quasars?
Well, yes. This one certainly, right? So, okay, so I have no time now to speak about this. This is absolutely crucial. So, in the proof, is that there exists a Mukai model of M8. Mukai has constructed a model of M8, which is obtained from the Grassmannian G26. Right? So, I mean, to prove such a theorem, of course, I mean, something exceptional must happen for genus 8, and this exceptional thing is the Mukai model. So, this sits inside P14. And what Mukai showed was that a generic curve of genus 8 is, so for any C in genus 8, actually he proved a very precise theorem. For any curve of genus 8 which does not have a septic model, there exists a 7-dimensional space. Yeah, I should decide myself whether I do affine or projective. Let's do projective. Yeah, a G714, such that the intersection of the Grassmannian, C is the intersection of the Grassmannian with this plane. And then, of course, this is embedded, so this is P7. This is embedded as the canonical linear system by the junction formula. So if you wish, you can have this Mukai model of M8, and I will denote it by MM8, right? So it's Mukai model of M8. So this is really it's a GIT quotient, it's the space of the Grassmannian. Yeah, so let's call this 6-dimensional vector space V. It is the Grassmannian of affine 8 planes inside wedge 2 of V. And then, of course, there is a natural GIT action of SLV. And you take the GIT quotient. So this is a birational model of M8. And there is a map from M8 to MM8, which contracts this divisor of septics to a point, in fact. Right? So there is a map which contracts. So in some sense, this explains the second part of the proof. It does not explain the theta null thing. Essentially, the point is that we sort of what we do is that we know that any curve via this Mukai construction, any curve of genus 8 will sit on a P7. And now we look at this P7, so it's a P7, and this sits inside P14, and we look at all the 8 planes containing this P7. Right? So this is a P6, a 6-dimensional bundle of planes, of 8 planes containing this P7. And we also know that this quadric, so the curve, if I take a generic point C eta in theta null, I have C lives inside a rank 3 quadric, Q0, inside this rank 3 quadric. This is a rank 3 quadric. And any quadric any such extension will correspond to a K3 surface containing the canonical curve. And you look at exactly those for which this quadric has rank 4. It can have rank 3, 4, or 5, and generically has rank 5. But you look at those which have rank 4, and then you get a very special B-elliptic K3 surface, a one-dimensional family of such K3 surfaces out of the 6-dimensional family of K3 surfaces containing C, and that produces this pencil. And it's a very remarkable pencil. It's a pencil which will have it will not be a Lefschetz pencil. It will have 2 special fibers which are like this, which are kind of elliptic curves, 2 elliptic curves meeting in 1, 2, 3, 4, 5, 6, 7 points. But in any case, it does not intersect the other divisor. So I don't have time to explain this last part of the proof, but essentially it uses a lot of facts that only happen in genus 8. And it produces this example of a Calabi-Yau moduli space, which is a quite natural moduli space. It's not something artificial. So thank you very much.